Welcome to lecture 4. As I said, we're kind of halfway through our program. Recurrent neural networks. Raise your hand if you know recurrent neural networks. You heard of them? Even if you just heard of them, I'm not just going to ask you to explain them in front of the class. Okay. Okay, so hopefully today is easy peasy. So today, we see the abstraction of what RNN is. So we learn about this thing called neural networks, which is a model which frees us from a huge limitation of the previous ones, the previous models we saw, which is we work with a constrained input size. The input is always the same size, okay? We get rid of that. We also see simple RNN architectures. This is also called an L-man network. So we're going to see the most basic RNN you can implement, why it's cool and why it's bad. And then we see gated architecture. So if you're familiar with LSTMs, stuff like that. So we explore the concept of gates, hard and soft gates, to see what that is. We unlock even more powerful recurrent neural networks. So let's start. Abstraction of an RNN. What is an RNN? But first, we start with the motivation. You saw it already. We saw various ways of modeling your input data, but there's always one thing which is the same. We need to know the input dimensionality. We have that D in whatever, a certain element, amount of elements with that dimensionality. So it's test fixed. Is this realistic? Can you tell me a case in which this might be bad? To always assume we have, I don't know, 10 elements, 20 elements. Yeah.
In general, like sentences are not.
Yeah. Sentences are they are not always the same length. Someone else? Anything that comes into mind? Okay. Well, that's pretty much it, right? Sentences can vary in size. Also, if you have the data which has a specific sequential relationship, for example, stock prices, this kind of messy because different stock will have different number of data points. Like, for example, you may have the stocks of Apple, which have a lot of dense data because it's been existing for a long time, but maybe a startup that existed for the last 6 months doesn't have so. Another thing we need to talk about is memory, because so far it makes sense that when you solve a task, you want to have a concept of memory, right? What we saw in the past, but not everything is necessarily relevant, right? So far, we assume that the memory is somewhere in the parameters. We keep training the model, and somehow that can be seen as a memory, but we never explicitly model this. Also, I want to add something which just came to my mind. Someone may argue, when we say that sentences can vary in size, you could say, yes, Simone, I can fix that. I can, set a max sequence length. I don't know, like 200, because for me, more than 200 almost never occur. And then I do something like padding, which basically the cat is on the table, pad until I reach size 200. And so now all my sentences are 200. That works. It's kind of a clever hack, but mostly it doesn't. It's a huge limitation. It was a thing that we did in the past. It worked, but in the sense that you trained the model somehow, you got around the problem, but it wasn't really great. Today we see how we can actually achieve proper varying length. So,
One question about
when
you talk about the sequential data, is that the same as continuous data, or is that
continuous
data, like time and that it can be infinitely divided into smaller chunks?
Okay, so your colleague asks if sequential data is the same as continuous data, so an interval of data can be continuously more and more divided. No, not really. That's like an interval. We're talking about like time series, for example. So continuous as if there is a ratio, it's like chronological, something that depends, right? Okay, so there's no other stuff. Let's go. So with abstraction of an RNN, so we have our usual sequence of input. It may be, n elements, x1, x2, blah, blah. And each vector has the same size. B in, so like every element has the same dimensionality, like 300 dimension, 50 dimensions, whatever. So what might be in the element of input at position I. So this could be a word embedding for the token I, it could be some one-hot encoding, we don't really care, it's whatever we saw before as an input. We then have a single output, which is a D-out dimensional vector, our usual yn. And this is obtained by processing the whole input sequence. So for example, you may say process an entire sentence, token by token, and get a label, sentiment analysis, for example. RNN is a function from an input to an output. So we're going to say that yn is this RNN function of the input sequence. And we don't know anything about that, but we're going to see what it is about. But first, let's talk a bit more about what this function does. So we said yn is the RNN mysterious function applied to the whole input, x1 to xn. If we assume that n is equal to 3, then our input is x1, x2, x3. We agree? We don't disagree on this? Okay. Then we have y3, which is RNN of x1, x2, x3. But if I don't process the last element, if I process only x1, x2, then I can also process those two elements, and I can get y2 equals to this mysterious RNN function applied to only x1 and x2. It's the same for y1, right? And the same for y4 if we have more than 3 elements. So, in fact, the RNN function outputs a vector yi at each position, and that's the thing. So let's call this sequence outputting function RNN star, RNN asterisks. So it's gonna say that y1 to n is this generic RNN star applied to the whole sequence, but without knowing about anything about the RNN. We don't know how it works, we don't know how it's implemented. What are the advantages? Well, you saw this, right? We can apply it at every single step and obtain an output at each step. Also, every time we apply RNN, we saw the whole task history. When we obtained y3, we saw x1, x2, x3. When we obtained y2, we saw x1 and x2. So we always say the task history up to the point we're calculating. So each output takes into account the entire history without any Markov property. And if the processing inside the RNN is somehow fixed and standardized, because I didn't say that y3 and y2 do something different. They might do completely different stuff to x1 versus x1 and x2 versus x1 and x2 and x3. But that's useless. If this is standardized, then we can recurrently apply the same thing over and over, just feeding progressively. Input, obtain something, input, obtain something. And this frees us from the requirement of fixed input size, because we're just reapplying the same block. What do we do once we obtain this y at any point? The usual. You can use it for further prediction. You can plug it into an NLP, into a softmax, into a sigmoid, do something with it, depending on your task. But between the two steps, we also talked about memory. So we need to have a concept of memory. Okay, so now we know that this RNN is some mysterious block that can be applied infinitely as much as we want. So that means that I can feed an arbitrary amount of inputs, and it doesn't matter because the RNN can be reapplied as long as I have tokens. So whether it is 1 word, 2 words, 3,000, I can keep applying it. But we also say it's important to model the memory. So how do we do this? So the RNN uses I misread. There was a typo. There's not a typo here. Uses the concept of state, which is a special vector which passes information across computation steps. So we call it SI. It has its own dimensionality because, again, still a vector. And at each state, we have the current input, xi, sorry, and the previous state. So the memory that we carry from the previous computation. And we compute the current state, which is the new memory, which takes into account the new information we saw. What's R? Because you see that SI is some R function of the previous state and the input. We'll find out later. Don't worry about it. One thing. So we have this state. So at each stage, I, we have I minus 1, and we compute I. What do we have at the beginning of the computation? Where we didn't process anything. What is a S0? The first ever state. Anyone wants to guess or knows? Yeah. No, it's not the starting sentence, because the start of the sentence, we'll use it for the input. This is a state, it's some vector, dense vector, which represent the memory. Yeah?
I would personally like to do zero vector, but
yeah, it's exactly that. It's a zero vector. You may argue, you may also initialize it randomly. I guess that could be done, but zero makes more sense because we have no memory at all. We didn't see anything. So yeah, the initial state is 0. So let's make this a bit more clear, okay? We have these couple of functions. Oh no, sorry, I forgot. We also need the output. Silly. I'm stupid. So besides the state, we also need to compute the actual output of the network. So again, at each state we have, again, the input, the state from the previous calculation, and we calculate the current state, as we said, and the output. What's all? Again, we'll find that later. So for now, don't worry about it. And this completes our abstraction of RNN. Now you see how we can feed to the network our input AX feed also the previous state, which is either 0 if we're starting, or the status we calculated the previous step, and keep doing this. So the state we calculated becomes the previous state of the next stage, right? And we obtain also the output. So far, anything? Yes? You're a bit ahead, yes. In many recurrent neural networks, the output is also the state, but not necessarily. You may want to keep them separated because the state you want to isolate it as a memory, and with the output you want to do something else. It really depends what you do inside of RNO. So there's not a definite answer, right? Anyone? Yes?
When you said it's not Markovian, but you only get the previous state vector, what's like, isn't that Markovian to be previous state, other state before that are?
Okay, your colleague asked, how is it not Markovian if I'm taking into account the previous state? It's not Markovian because the Markovian assumption we have in the previous model is that word 3 depends on, no, 3 is too short, sorry, word 10 depends on the 3 previous words. So word 9, 8, 7, okay? This is not Si minus K, is always the previous one. So I will calculate the first one, then the second one, then the third one, then the fourth one, and the state gets increasingly accumulated by the processing of all these. Is that clear?
Yeah, yes, I thought Markovian probability meant that like if we have the previous state, all other states before that are.
No. It's a Markovian assumption. So since it's too expensive in the previous model to calculate the probability of word 3000 given the 2999, we assume it depends on your from a finite window. It's a limitation, it's an extreme simplification, but we got away the problem. Yes?
This state kind of doing the same, having the same purpose. I mean, it accumulates the state, I guess, from the sentence, right? I mean, up to that point. So it contains it should contain the relevant information of the previous word.
I don't get which one is the question. Yeah, it's correct what you're saying. That's how our state works, but what's the question?
Right.
Okay, you will say it's still Markovian, but it is the way. There's not a Markovian assumption because if this was a Markovian assumption, this will be, I don't know, Sy minus K, which means at some point I have some way of erasing, I have a sliding window of the last 3 or 5, but no, that's everything. The whole story from 0 to 1,000,000, that can be S 1,000,000, 900,000, before million. There was another question, I think. Yes?
In the current state, you have a typo there in the R formula RSI minus I minus 1, right?
Yeah, we got. I need to start taking prizes for spotting the typo. It's not I minus I. Sorry, of course, this is I minus 1. Is a typo. Yes.
Haven't really defined this data over here. But the weights of the model, or
That's the weights of the model.
and all functions.
You mean theta?
Yeah, data.
Okay, theta is not defined by is the parameters. There will be. We'll see what it is. There are the usual weights and biases. You know, our matrices. They do nice things when we learn. And RNO is a mystery. We'll see it in a bit what they do. Yes.
What did you say about the Markov assumption? I think it probably is very confusing the words with the states. So like in here, the state is accumulating the number from all previous words of this theory. So we don't have Markov in that sense. While in the diagram model or N-gram model, we have the assumption. When you look at N words, there's like words and states.
Yeah, that makes sense. So basically in the N-gram model, the Markov assumption is actually applied to the actual words. The state is some kind of memory, but the state also takes into account the input. So you may argue also apply to words. It's just that, guys, that the Markov assumption is not here because this can be applied forever. There's no moment in which I cut and I say, okay, no, sorry, apply it only from 5 words before. This is from the start to the end. If there's nothing else, okay, cool. Then we can move. Now, I want to show you an alternative visualization of the RNN. So let's start from the input. Well, let's say we have this input of 4 tokens, so 4 elements. We add our cell, this is an RNN cell, which take the initial state, which again, this is only 0. We didn't see anything. It produces a new state and a new output. Now, this state gets passed to the next RNN cell, which produces a state and an output. This gets passed again to the next RNN cell, which does something, which I don't know, again, produces a state and an output. And we go like this. Now, 2 things we need to clarify, first of all. The parameters is shared. It's not like these things are different elements that have different parameters, different matrices of weights, different biases. And also, this is not how an RNN is implemented. This is only a visualization, but we will have only one of these, and it gets applied continuously. When you define, you go to PyTorch or PyTorch TensorFlow, whatever you use, and define RNN, you just decide one cell, and that cell can be applied over and over and over and over. So the actual more correct representation is the previous one. I cannot show you, but whatever, I'll go back. This one, it just keeps going. Well, this is more like to make you get an idea of what's happening. Now, we're also gonna see 2 different kinds of RNNs. First one is called an acceptor RNN, and it kind of looks the same, but now we're also using it for an NLP task. So to calculate the loss, we're gonna plug the final output of the network into whatever you want, a softmax, and it depends on your task. That's your total prediction, and then you compare it with the gold level and calculate a loss. So the loss is computed on the final output. So this kind of makes sense when the intermediate outputs, you know, they're necessary somehow. Maybe you can do something with it, or you just discard them. But the final output is what matters in your task. This is called an acceptor because it kind of works as if, you know, processing an entire sequences and producing a final label like 0, 1, so accept or reject. But do not get tricked by the name. It's not only for binary tasks. That can be a softmax, so you can be, you know, an RNN that processes an entire sequence and produces a distributional probability across 20 labels if you want. It's just how people call it. Another alternative you may think about it is just the opposite, is a transducer RNN. The transducer RNN does what we saw before, but at every single step. So the first output, with which in here we're calling Z1, is gonna be plugged into your activation function and compared with a specific label. We're gonna do the same here, the same here, the same here, and then we're gonna combine them. Typically we sum them. We may average them, we may weight them, it depends on the task. It's cool for sequence tagging. For example, you know, you want to understand the what's the name? Part of speech tagging. What is a verb? What is an adjective? What is a noun? Blah, blah, blah. So overall, you sum the losses. So far, yes?
This theory, I could just run it, take the loss, retrain to like train it in that step, and then run it again, train it some further. I mean, I could train it at every step, right?
So why do we need to sum the losses? The first easiest question I can do, because it's done like that, and I didn't invent it, and it works. Now, if I have to speculate and go a bit more philosophical, remember, this is just a representation. There are not 4 cells. There are 1 cell that gets applied over and over. Now, if you ask me if I need to calculate how bad I am in tagging a sequence, not a word, a sequence, I want to see everything, right? Because then I want to backpropagate to my parameter something which tells me something about the whole sequence. So make sense intuitively? Something, yes?
I didn't catch what is MLP.
Multi-layer perceptron, full feed-forward a neural network, basically. You pass it, make some prediction to it. Yes?
Part speech tagging and name identity issue. I think we also need to use bidirectional.
You're a bit ahead of the lecture. Yes.
About the S4, does it turns back to like?
Not in this case. In this case, S4 is not doesn't. This is just a simple one. Okay, but we're gonna see. In fact, you're exactly ahead of one slide. Yes. Is the softmax shown? Sorry. And a bad night is a softmax function that we saw in the previous lecture. So basically, you pass a vector to it and it converts into a distribution of probability. So it will tell you that basically this element has probability 0.3, 0. Another 0.1, and they all sum up to 1. And usually you pick the element with the highest probability, and that's your prediction. Okay? It's kind of like an extension of sigmoid. Remember, sigmoid maps between 0 and 1. But we cannot apply sigmoid to a vector because the numbers then sum up to 1. Okay? Can I go or? Okay. Now, as your colleague was saying, we have bidirectional RNN. Now we have our nice input, and we do our usual stuff. So we have our cell, which again is 1, but I need to show you. Be wary of this. Notice it's called theta forward. So we're gonna compute our state and output, our state and output, our state and output, our state and output. Then what I'm gonna do is do the opposite. So I'm gonna have another RNN which goes backward, which gonna start from the last token. I'm gonna compute a state and output, a state and output, a state and output, a state and output, and then I'm gonna combine these 2 final prediction, which is y for left to right and y for right to left. Combine them so how? Typically we concatenate them. Again, you may sum them, you may average them, you may use some fancy weighting, it depends. And now we plug it to our usual activation function, calculate the loss. So the idea is simple. You run 1 RNN left to right and 1 RNN right to left. These times we actually have 2 network. So these are still 1 cell, but 1 cell for one direction and 1 cell for another direction. Yes?
Just want to know that like it's kind of looking from the future of this content.
You're right, it's looking from the future.
And so the validation is okay. Like
we'll see why it's why sometimes we need to look to the future. Give me a second. So the idea is simple. When it's good, so because your colleague rightly said, but isn't cheating we'll look into the future depending what we're doing? Well, depends. If you give me something like part of speech tagging, sometimes whether something is a verb or not depends on the words after, right? So I need to look at what's after, because when I need to look at the whole sequence as a whole, it's useful. It's bad when you're cheating. For example, autocomplete. It also probably wouldn't work, because if you train a model on autocomplete and can see already the full sequence where you actually use it when there's no full sequence, it just wouldn't work. So yes.
So if you actually wanted to do plus tagging with the setup, then we don't only have to put together y4 from both directions, but also y3, y2, y1.
So the answer is we shouldn't have to use only the final token, but we should use the other one. It depends how you frame your task. Again, I'm gonna appeal to authority and say they do it like that, so it works. But also, again, intuitively, well, you're actually right, because this is an acceptor. So the path of speech tagging is just an example. Yes, I think I agree with you. I will argue if you're doing actual path of speech tagging, you will need a transducer by RNN. So that means that you do something with each of these, because after all, you're tagging every single token, right? It's not a cumulative sentence, yes. But in this case, I didn't think about it and I put an acceptor because it was for last year's slides. Okay, yes?
Like when you want to like overcome from cheating, so should we like this tokenize have some limitation between the mass tokenized and the inverse tokenized? Should we have something like some limitation or things behind these two, like not kind of overcome like not cheating?
So your colleague said, can we overcome the cheating thing by using some post-hoc implementation? What about an even better things? We don't cheat, and we don't use networks that are not fit for the task, right? Okay, I will say just you don't cheat, huh? Okay, that's even better. Then if you can, fix it in post-production, okay, but it's extra work. You still train a model, it's a bit messy. Yeah, someone? Yes.
So these are actually the same model architecture. One's run with
They're exactly the same model. It's just the one runs left to right, and one runs right to left. Again, can you implement them differently? Yes, typically it's the same. Okay. Yes.
add to this that they have different weights for the forward and backward run, so not they're not identical, they're maybe the same architecture, but they're slight nuances.
Your colleague is right. The parameters are different, backward and forward. So indeed, they are not the same network. But I was talking architecturally. They have the same activation function. They do the same linear combination. But of course, they initialize with different matrices and different bias vector, so they change. Also, they process different stuff, right? One goes left to right, one goes right to left. So the back propagation is gonna move differently. Okay. Now we saw a lot of abstraction. Let's move to something actually concrete. So how do we implement this? Hellman's network. This is the simplest RNN you can implement. And your colleague was right that the output is indeed the state. So how do we calculate the state? The function that we called R before. Well, we do our usual fancy linear combination. You can see that we have WS, which is a matrix of weights specifically for the states, and a matrix of weights specifically for the input. So now we're actually doubling the number of parameters and the bias vector. And then we're gonna plug these through our fancy nonlinearity. Why? Because at this point we understood the text is complex, so nonlinear is pretty much always the case. And the nonlinearity is usually the hyperbolic tangent or ReLU. If you check the hyperbolic tangent chart, is kind of similar to the sigmoid, even if it's zero centered and actually between -1 and 1. Yes?
Are the parameters for the state trained, or are they adjusting like during the run of the RNN?
Do you mean adjusted during the run?
So
all you see here, it's trained traditionally. Backpropagation, you feed your key couplet in the rows, backpropagate, you change the values, and then you stop when you run out of computation or you reach a good loss. It's just a normal parameter, just more of them. Okay. Yes.
Way different from what we did before, right? Kind of did an operation you move the points, and then we're trying to backward propagate through the network, through the weights we had before we updated them, right?
Yeah. So your colleague is a bit confused on how do we train this? Is exactly the same thing. Actually, later on we're gonna see a full backpropagation of a TOI RNN, which is root exam relevant. So relax. And you're gonna see there is exactly the same thing. We start from the loss, we could build the computational graph, we calculate the local and global derivatives, and we backpropagate exactly the same way. Yes?
still need to know how we ran the RNN for that, right?
No, you do not need to know for how long it runs because before backpropagating, you need to stop processing the sentence. So you arrive to the end. Doesn't matter if it was 5 tokens, 10 tokens, or 300. Also, it makes sense, right? Because across an entire data set, which may have sentences of 1 word or 20 words, you average over. You learn some kind of general representation, so you average over the population.
Yeah.
So, yes?
And isn't it important how many times we ran it? I thought this is exactly why we have the vanishing gradient problem. As we run this 100 times, we take the matrix times or to the power of 100, and then the eigenvalue is 1 or negative 1, we have the exploding or diminishing gradients.
Your colleague is ahead of the lecture and just rightly points out by running so many times, don't we risk vanishing or exploding gradients? Yes, indeed we do. We're gonna see how we can fix that later. But you're right, it happens. Yes?
So y(phi) is like a function of S(phi), which is all
Sorry, what? Which one? You said
like the line saying y(phi) equal to S(phi). Right.
as of I. So sorry, I didn't understand you. Can you please repeat? Sorry.
Yeah, the second one.
Yeah, O.
Yeah.
The O function.
O is also like a linear transformation.
No, O is not a linear transformation. I see is exactly an identity function. O of SI is SI. The Hellman network doesn't do anything with the state and just says, that's my output. So as your colleague was saying before, the state and the output are the same in this case. Does nothing. If there will be something, I would have wrote you W whatever. Yes?
I do understand correctly that weights for X are trained on the input tokens, or where do we get the weights for X?
So your colleague is asking, am I correct to assume that the matrix WX is trained on the input and WS is stable state? Yes or no? That will arise from learning, but backpropagation, it's all together, but it's multiplied by the input. So you may argue that it takes more stimuli from the input.
Yeah, it's just I don't understand where there's also the matrix or weights for the state comes from.
What do you mean where they come from?
Like weights, like they do not get updated as we go through the recurrent network. So
Well, they get updated after you run the whole sequence and backpropagate during training.
so
you first process the whole sentence.
So this recurrent network does update both, right?
Yes.
Okay.
Yes. It updates all the parameters. Yes. Anything else? Okay. Full of questions today. Okay. So has your also a lot of futures here today, because as your colleague was saying again, we have a problem with RNNs. The problem of vanishing gradient when our gradient becomes close to 0 or infinitely small. We saw this before as well. Or exploding gradient, where the gradient becomes very, very large. In both cases, we are screwed because our learning is basically ruined. If we have a vanishing gradient, we're gonna start to move, change our weights very, very, very little. It's gonna take forever before we actually learn something. Exploding gradient, you just go bonkers. You keep changing completely, and again, it's a mess. It's especially severe in deeper networks. How deep? We don't know. It depends on the data, on the task. Empirically, I can tell you this from the papers. Usually up to 15 steps, fine, smooth sailing. 15 to 50, you may start noticing that your gradient becomes big or small enough to slow down, alter learning. 51 steps, bye. You can even get stuck and stop learning altogether. And as a consequence, we cannot have very deep RNNs. So it was very cool when people say, oh, this can potentially process millions of words, except it cannot because it collapses very quickly. So I prepared a deep dive into how this works, just to give you guys the intuition. Nobody will ask you to do anything remotely as complex as this, okay? You're gonna be probably asked in the exam to do a computational graph, but go back to lecture 1 and 2. That's the complexity of the function we're dealing with. This is for you to understand. So this is the backpropagation of a toy RNN, which does 2 steps. So again, what I want I might have an extra slide later from the out, whatever. What I want you to notice is that using the hyperbolic tangent, where is it? Yeah, it's like here, it's like here. Okay, so this is our nonlinearity. Now, this means that at some point we're gonna multiply stuff for the derivative of the hyperbolic tangent. And now the hyperbolic tangent is this very cool function, very good function, which converses great, it empirically works great for learning. So that's why it's a common choice. Also, it's a smooth increasing function, which we like, as a smooth gradient, which tells us where to go. The problem is that as you increase or decrease the values of the tangent, you get progressively closer to zero. You never touch it, but you get more and more closer to zero. Now, what happens when we multiply a value which is smaller than 1 for another value? Yes? It gets smaller, it shrinks. So yeah, we're multiplying for the derivative of the hyperbolic tangent, which is a number often smaller than 0, by another number, and it shrinks. But guess what? We're also doing it here, and that's already the shrink value, because you see that first we obtain sigma 2, that's how I call it, then we multiply sigma 2 by a matrix and by another derivative of the tangent. So we shrink a shrink number. You do it for enough steps, and you get the vanishing gradient. So that's why it's happening. What about the exploding gradient? Well, that happens if the values in our matrix is progressively larger. So if they start increasing uncontrollably, it doesn't matter how much you shrink them. You know, if you try and shrink 200,000 by a bit, it's still a huge, huge number. So that's why we have vanishing exploding gradient. And we're going to also see how we can solve it. Any question? Yes?
So vanishing gradient and exploding gradients have two entirely different mechanisms.
Yeah, vanishing and exploding gradient, there are two different things that can happen in the same network. It really depends how your learning goes. Your values may start shrinking and then or they may start exploding. I think typically they don't happen consequently. You don't have like vanishing that's exploding, because once you shrink and it starts, it's gone. It's gone. Same if it starts increasing a lot, it's not gonna shrink at some point. So yeah.
I think I'm absolutely right. What does WX and WS represent?
Those are matrices of weight. So basically in an RNN, you know W, the matrix of weights parameter. Okay, an RNN has both a matrix multiplied by the state and a matrix multiplied by the input. So you're doubling the parameters. And then there's a bias vector.
There are separate parameters for the state also.
Yes, I mean, they're still merged into a linear combination. So the previous slide had WS times S plus WX times X plus B. So it's a linear combination of the two. Okay. So if you're happy with our RNN and their problems now, we can actually move to the quiz. Now we see gated architectures, which kind of solve the problem we saw so far, but also make a smarter use of memory. So recap, these are nice, shiny RNN, which is super powerful, but also super stupid because it collapses very quickly depending on what you're doing. Now, each state represents memory somehow. It's an abstraction. Every time we apply R, I'm excluding O because considering the network, O is just an identity, doesn't do anything. We read the current memory, so the state from the previous up to the previous computation. We read the current input. We operate them in some way, like the network does the fancy linear combination plus an hyperbolic tangent or ReLU. And we write the result to the new memory. But this is not controlled. We are just rewriting the entire memory every time. So that's a bit of a problem, because what if we wanted to rewrite only part of the memory? Well, there are like, something should stay as what it was before, but something should change, right? It makes sense. So let's see how we can have a more controlled access to the memory. Now, we have a memory vector, our usual S, and our input vector X. Now, consider a vector that we're going to call a gate, which has only zeros or ones, okay? Then we introduce our dear friend, the Hadamard product, which is just a fancy way to say element-wise multiplication. Now, we're gonna introduce the gates. We're gonna say that our new state is the gate times the input plus the opposite, the complementary of the gate times the state, which means that every entry of the new state comes either from the input x when the value of the gate is 1, or from the memory state when the value of the gate is 0. And this means that through a gate, we can rewrite only part of the memory. And we're going to see a practical example now. So consider this vector x 10, 11, 12, this gate 0, 1, 0, and this state 8, 9, 3. Then we're gonna do g Hadamard x, however you want to pronounce it, plus 1 minus g Hadamard s. And you see that the first time, these are 0, so it's gonna not let these, but this is gonna come, and then it's gonna block these and let this through. So in fact, we obtain 8, 11, 3. Is it all clear why we obtain 8, 11, 3? Yes?
But we compute that we take x s I minus 1 like the previous state, because this way we are kind of randomly selecting from part of x be like written to the state instead of the state being modified to get a new state, right?
Yeah. So we are actually, instead of modifying before with a fancy combination, we're just passing to the gate and selecting specific elements. Yeah, that's the idea. That's the idea. You're just filtering and combining, okay? Any other? Yes?
Are these gates similar to the ones used in LSTMs?
We're gonna talk about LSTM in a couple of slides. So yeah, you're gonna receive your answer. Yes?
Assume that the elements in vector x and vector s that correspond to each other. First element is vector s corresponds to the first element vector s.
No. No, they should not correspond. It's purely a filter. There's no assumption about what is in x and s. It's purely a gate.
Say I forget the first element of input x, but I take the first element of the memory s.
Yeah. Then it's messy, isn't it? It's a problem.
It should be aligned, right? Information should.
Okay, now you're onto something. So your colleague said it's kind of messy because I should have some understanding what is in x and s. Otherwise, how can I be sure that I should always ignore the first and third element of x and always let in that? That's one of the limitations of these gates. So we can handle the memory more efficiently, but the issue is that these are called hard gates. They are predefined, they are fixed, and we just have to hope that they work. Or even worse, we have to do some very careful feature analysis to decide heuristically the best value. So what I propose is make it a learnable parameter. So you just plug into the loss function and the network learns how to change these values. So this is not anymore 0 or 1, but it's every possible value between 0 and 1, which means you can kind of interpret it as like, I don't know, 0.25 plus a quarter of that element of the input, or 0.75 plus 3/4 of that specific element of the input, but it's learnable. So you can actually learn the better values. Sense? Either you're scared or you're very, very knowledgeable about this. And LSTM, which is called long short-term memory network, is basically the most popular example of this. So, okay. So what do we know about the LSTM? They're made to solve the vanishing gradient issue, and they're the first model that introduces this gating mechanism. So how does it work? The LSTM splits the state in two vectors of equal size, so just split in half. One half is called long-term memory cell, and the other is called short-term working memory. Now, at each state of computation, when we need to produce Sj, we actually use two vectors, Cj, the long-term memory, so the full story, everything you saw since the beginning, and the short-term memory, which is only the relevant part of what you saw. So it's like you're keeping a book with everything you learned from the first word until now, and then you're keeping some pages, some of your more relevant pages that are helping you to process what you see right now, right? Which is kind of inspired how the brain works, right? You know, there is this mind model of the long, short-term memory and the working memory. So you have this long-term memory, it's everything you learn in your life, but the short-term is recalled at runtime to make you exist, right? When you run a bike, you need to remember how to run a bike, but you don't need to remember actively how to run a bike every time in your life, right? And there is a working memory, this kind of a bridge between these two is one of the possible interpretation of how memory works. Not claiming that it's drama, psychology or anything. But this is what inspired LSTMs. Now, at each input state J, this should be actually, this should be computing stage, whatever you get. At each stage, step J, we have three trainable gates, which decides how much of the new input and the old memory you write to the new memory, and how much of the current memory should influence the next output. These are called the input gate, the forget gate, and the output gate. And you don't need to know anything else besides this, but since I am stubborn, I'm still going to show you how it works. Yes?
Why do we split the state vector into two halves? Why not just keep two separate vectors?
It will be the same. It's an abstraction. So your colleagues ask, why do we split? Why don't we keep two separate vectors? In fact, we did. The split is just a way of saying, you know.
So it's not like the first half of the variables are the short term, long term is just two vectors.
It depends on the implementation. You might keep them completely separate. You might decide to combine it at some point, but in theory, you keep them separate because the long term is supposed to, you know, incorporate something which is also in the long term. The short term should be part of the long term or influenced by it. Okay, then I'll move on. So, deep dive into how an LSTM works, if I even remember how, because this thing I need to restart it every year, to be honest. So, you have the input, X, and you have the relevant history, H of J minus 1, and then you have the full story. So, everything you know, so relevant pages, and the new input. First of all, we need to do one thing, understand what new information we can capture. And for this, there's no gate, we just do our fancy linear transformation with a nonlinearity, which means we're gonna put the input, the relevant story, so the short-term memory, combine them with our parameters and pass them to an hyperbolic tangent. This is all new information, it's a computation, nothing new compared to the previous networks. But then, now we have new information, and we need to make up some space to memorize it, right? Because again, we cannot wipe the whole memory again, we're past that. So we need, guess what? A gate. So we have a forget gate, which again takes the input and the relevant story, the short-term memory, and learns a gate to free up some space. Now, look at this. We have a tangent here, because that's information, but we have a sigmoid here, because a sigmoid maps your values between 0 and 1. The result of this is going to be a vector, and the sigmoid is applied to every single element of a vector. You might remember that in previous lecture we said, oh, we don't use sigmoid on a vector, we use softmax. Yes, but here we use a sigmoid because we don't want a distributional probability. We want just a number of cells. They could all be 1 if we want to. It will be a gate that passes all the information. So that's why we use a sigmoid. Then we learn how to free up some memory. We also need a way to let in new stuff they want to memorize, to fill that empty space. Guess what? We have a gate. It does exactly the same thing. So again, you will have your H shorter memory, your input, pass it through some matrix of weights, gonna sum them, so it's a linear combination, and again, another sigmoid. So you have another gate. Now, before moving to the next step of, the other gate, you may remember there's 3, we want to obtain the new full memory. so the long-term memory. So that's the new version of this. And to do that, we're gonna combine the gates. So this is the other art product. So we're gonna pass the full memory through the forget the gate. This frees up some space. Then we're gonna sum up the input gate combined by the new information, which basically say, okay, erase a bit of the long-term memory, decide how much of Z we want to learn, then sum up the two vectors. That's how we obtain the new full book of our life, okay? And then we need one final thing, how to calculate the new short memory. How do we extract the relevant page? Guess what? We have this, but we have a gate for that. So again, we pass into a sigmoid. We have again the shorter memory, the input. We learn a gate that tell us, okay, given the full memory, the long-term memory, how to extract some relevant pages that are interesting for me with the usual Adamar product. So we pass it through the gate and we obtain the new short-term memory, which is also the output. So just like in a L1 network, the new short-term memory is also the output. All these things, all these huge amount of parameters has all their own dimensionalities that I don't care particularly about. H is the dimensionality of the hidden ledger. So again, I have the parameter. And as I said before, notice the activation function. When we are setting up a gate has only values between 0 and 1. 1 completely passes through that specific element of the vector, 0 completely blocks it. And so we use sigmoid for the tree gate. And the hyperbolic tangent indeed is good for new information. It's kind of like when we use a ReLU or a GELU or whatever. Yes?
Always forget because we have this at the sigma, even in the hyperbolic they never reach one fully.
Okay, so your colleague says basically they cannot reach one fully because the hyperbolic tangent goes only to that. No, actually no, because the gates have a sigmoid, not a hyperbolic tangent. So these are values of the information, these are the gates, and the sigmoid can indeed reach one. So also we might have some post-processing, like if it's 0.098 mapping to 1 or whatever. So yeah. Anyway, this is the way that LSTM works. This is also the way I'm gonna say goodbye to you, and I'll see you next week, and good luck with the homework.